Hello everyone. Today we are going to look at the first problem of this year's BMO round 2. So the problem states that for any two positive integers m and n, we're going to define their lowest common multiple and highest common factor. And essentially we want k to denote the number of ordered pairs of positive integers satisfying the equation such that their least common multiple plus their highest common factor is equal to the fourth power of prime. And we wish to find the smallest value of k for all prime p is greater than 3. So normally I would start to write the, essentially we want to rewrite m and n into the form of the highest common factor. So for my working, I'm going to use the notation GCD to denote H M N because it is the conventional way to do it. So we could let GCD M and N be D. So we are able to rewrite M and N in terms of D. So let's say M equals D times capital M, N equals D times capital N. And we know that M and N are coprime. So they do not share a common factor that is greater than 1. So by definition of the lowest common multiple, and this is just equivalent to our mn in the question, we could write lowest common multiple of m and n as d times m and n, both capitalized. So now we have the expression for the lowest common multiple and the highest common factor, and we can rewrite the given equation in the problem. So basically d plus dm n equal to the fourth power of a prime. And we can factorize the left-hand side to give d times m plus 1, both capitalized, equal to p to the power 4. Now we have to remember that first of all, m plus 1 has to be greater than 1 because both m and n should be a positive integer. So therefore, it's impossible for d to be p to the power 4. And given that prime, the only possible factors for p to the power 4 is either p to the power of 0, which is 1, p to the power of 1, p to the power of 2, and p to the power of 3. And it's not possible for it to have p to the power of 4 because we already know that d cannot be p to the power of 4. So we can actually just discuss case by case. So it is helpful to write a table. So we could see when d equals 1, p squared, and p cubed. And we can see the relative value for mn. So for mn, when d equals 1, it would be p to the power of 4 minus 1, and then p to the power of 3 minus 1 when d equals p. And similarly, we have p to the power of 2 minus 1 and p minus 1. So we are trying to find the number of ordered pairs. So we can actually temporarily ignore the question where we don't have to find the minimum value of k because we want to play around with the question a bit more before we start anything. So if we can find an expression for m and n, that basically means we have found the lowercase letter m and n given the question. So now we have really transferred the problem into finding the ordered pairs of positive integers capital M and capital N instead of the lowercase m and n in the question. So one way to find the factor is to factorize the given expression. We could see that p to the power of 4 minus 1 equals p minus 1 times p plus 1 times p squared plus 1. And p to the power of 3 minus 1 would be p minus 1 times p squared plus p plus 1. And this one is just difference of 2 squares. And we don't have to do anything for the last one. So now we can really think about minimizing the value of k. So we could take p to the power 4 minus 1 as an example. If somehow all three of these factors are prime numbers, then it is really easy for us to determine the expression for m and n, because essentially we want m and n to be coprime. So this means that if we write m equals f1 times f2 times f3 to the power of p3, and n equals g1 times g2 to the power of q2 times g3 to the power of q3 times blah, blah, blah. We don't, for any I and j, we do not want fi equals gi. So if both three are primes, then the possible choices for capital M and capital N will be minimized. And that is exactly what we want to show. Now, in real cases, this might not be the case. For example, we could try the smallest example given in the question. So we know that p has to be bigger than 3 and it has to be a prime. So the minimal case would be p to the power of 5. What happens with p to the power of 5? We could work out. So 624 equals 4 times 6 times 26 as given in the expression. Now, none of 4, 6, and 26 are actually a prime because they're all even. But we can rewrite 624 as 2 to the power of 4 times 3 times 13, which gives us 3 distinct primes. Well, not really primes, but note how if we have to allocate the factors for m and n, 2 to the power of 4 have to be totally given to either m or n. That is to say, we cannot split 2 to the power of 2 equally into both letters. So for example, if I start with m equals 2 to the power of 2 times something, and n equals 2 to the power of 2 times something, then we know that the greatest common divisor of m and n has to be at least 4, which contradicts with what we stated in the beginning. They have to be coprime. So my point is, we have to give 2 to the power of 4 completely to one letter. And really, this has zero difference with a singular prime like 3. So we could calculate the possible ordered number of pairs of capital M and capital N in this case. Well, we have 3 factors, and they either go to M or go to N. The choices are independent. So if each letter has 2 choices, we have 3 factors. So that would be 2 to the power of 3, which is 8 different possibilities. And in fact, we could generalize. If we have n distinct prime factors where their exponent does not matter, the number of ordered pairs of m and n would just be 2 to the power of n. And I would like to just put this because we need this later. So now we really want to just find the ordered number of pairs of capital M and capital N. We just need to find the number of distinct prime factors of the given expression. And in this case, when p equals 5, p to the power of 4 minus 1, which is 624, has 3 distinct prime factors. I'm just going to write distinct prime factors, DPF, as an abbreviation to save time, and that is 3. Let's see what happens with p to the power of 3 minus 1. So this would be 124 equals 4 times 31, which equals 2 to the power of 2 times 31. So we know we have two distinct prime factors, and therefore the number of ordered pair m and n would just be 2 to the power of 2. I'm just going to write 2 to the power of 3 here. Similarly, we can carry this out for the last two rows. So we have 24, which equals 2 to the power of 3 times 3. So we could put 2 here and 2 to the power of 2 here. And finally, we have 4, which is 2 to the power of 2. And it only has one distinct prime factor in this case. And that is 2 to the power of 1. So we have actually just calculated what happens when p equals 5. The number of ordered pairs should be the sum of these four numbers. Which is 18 in this case. Now, if we think carefully about what we've done here, what is the minimum number of distinct prime factors when an expression can be factorized into 3 brackets? Well, it has to be 3, because let's suppose that the distinct prime factors is less than the number of brackets being expanded. Then this is clearly not possible, because you must have merged 2 brackets or more at some point, meaning that that number is going to be composite instead of being prime. So we can see here that p to the power of 4 minus 1 is expanded into 3 different factors in terms of p, and this distinct prime factor is 3, so it is actually a minimum. And we can carry out the same process for the rest 3 rows, and we will realize that when p equals 5, this is the exact minimum case we want, because if all the distinct prime factors are at minimum, then we know that between these 2 columns, there's a relationship of 2 to the power of n. So the number of minimum pairs of m and n must be at minimum as well. So we have already answered the question. When p equals 5, the minimum number of ordered pairs is actually 18. And that is the solution to the problem. Now, I don't want to just stop there, because the whole working seems like a bit of a coincidence. Now, in fact, this is a natural way of working, but I just want to do a bit of further investigation on what happens when p equals 7, p equals 11, and can we obtain the next minimum when we have a different value of p? Now, to answer this problem, using an Olympiad approach would be slightly difficult. Now, when I first see this problem, my instinct is that the distinct number of prime factors can be put into a different perspective, which is we can use the idea of analytic number theory to solve this problem. I first want to rewrite the number of distinct prime factors just to save time. We define the function omega n for all positive integers n. And this is basically the number of distinct prime factors as above. Now, this is the standard way to express the number of distinct prime factors. What we have done in the previous working is that we try to work out the value of this counting function. Let me just put dummy variable I equals 0 here. And then we're essentially trying to find 2 to the power of omega p to the power of 4 minus I minus 1. Now, this could be a bit of a jump, so let's just put the original value back to see what happens. When p equals 5, we try to find the value of k5, and that is Well, if we break down the summation thing symbol into bits, that is 2 to the power of omega. Well, that is 5 to the power of 4 minus 1, which we have done here. This is just the 624-bit. So that is actually just 3 plus 2 to the power of omega, 5 to the power of minus 3 minus 3 minus 1, which is 2. Then we can carry out the rest 2 rows. And that gives us 18. Now, with the function omega n, we could apply a known result called the Hardy-Ramanujan's theorem. It states that for most n, the normal order of omega n is roughly ln n. Here the ln would be a natural log. To understand this statement, a simple way to explain this would be very likely if we pick any positive integer, then the value of the function omega n could be approximated as a double logarithm of the number itself. Now, it is interesting that we have introduced a phrase called for most, because this is not true for all integers. A very obvious example would be if we try to work out the value of, let's say, 65,536. Well, that simply is just not possible, because the value of that, we know we can break that down to 2 to the power of 16, which means that the value of this function has to be 1 because it only has one distinct prime factor, and that is 2. And this is going to be far off compared to the value of double natural log of 65,536. But we can have a pretty good estimation. Now, we are not very familiar with the function omega n, but we must be able to do more analysis with the function on the right-hand side. We know that ln n grows unbounded, so it's infinitely increasing. So we could say that when n tends to infinity, the value of ln n tends to infinity as well. And in fact, for the double logarithm, when n increases, the double logarithm increases as well, meaning that this is actually equivalent to the original omega function increasing. So, what this tells us is that for the original counting function we have included above, which is this function, as we increase n, in theory, Kp should increase as well, because every time the exponent on 2 is increasing. So this should tend to infinity, and we should be able to expect a pretty quick growth, because it is like full exponential growth at operation at the same time. And in fact, this is true, that when we work out the value of K7, that is 24. Let me just write K5 is 18, as we've just worked out previously. K11 would be 44, and K13 would be 52. So we can pretty much expect that if we want to minimize the value of K, this is almost equivalent to minimize the value of P, which actually I think is a good way to explain why when we test out the smallest possible prime, we immediately get the smallest value of K. So it's not a pure coincidence. It is a pretty beautiful result. Now, I haven't given the complete proof because it is a very leaky explanation, because as we know, for most, this is not a very convincing proof probably to most people. And I certainly do not have enough time to fully explain and prove Hardy-Ramanujan's theorem. But I just thought this is a pretty fun exploration of this pretty good and pretty fun Olympiad problem. So, and that is the end of the video. So I hope you have enjoyed it. See you next time.